So let us understand the variation of G due to height, depth, rotation of Earth and bulging of Earth. So this is the Earth shown. This is the center of the Earth, which is the center of the sphere. This is the radius of the Earth. We label it as capital R. Let us say we were to move up above the surface of the Earth by a height h. Let us say this is the height h via which we moved above the surface of the Earth. Then we know that acceleration due to gravity at height h, g at height h, this is going to be given by g m upon r plus h the whole square. Now we can rewrite this particular expression. So this is the exact expression. We can rewrite it to be gm upon r square into r square upon r plus h the whole square. Gm upon r square is nothing but the acceleration due to gravity at the surface of the Earth. So basically I label it as G naught, and this particular quantity, I am going to invert and write it down as r plus h upon r whole raised to minus 2 is equal to G naught 1 minus h upon r whole raised to minus 2. So this is nothing but G at height h. So this happens to be the exact expression for acceleration due to gravity at height h. I will box this expression. So this happens to be the exact expression. Another exact expression is this. Now many times we encounter situations wherein h is less than r. H happens to be less than r. In such a case, we can use the binomial approximation, which basically states that 1 plus x raised to n is approximately equal to 1 plus nx. So this happens if mod of x is less than 1. So it's very less compared to 1. Let's say even lesser than 10% or 5% of 1. So when such a situation arises, we can write down acceleration due to gravity at height h, gh, to be approximately equal to g naught 1 minus 2h upon r. So the student can note that here the acceleration due to gravity is reducing compared to that on the surface of the Earth. Also, another thing to note is the index n over here happens to be minus 2. So minus 2 is being multiplied over here. So this is the approximate expression for acceleration due to gravity. So this particular expression is the approximate expression. Okay, so basically this is valid in the limit that h is less than capital R, the radius of the Earth. Now let us understand what would happen if we were to move inside the surface of the Earth to a depth d. Let us say we move inside to a depth d. So this is the center of the Earth. The distance from the center of the Earth to the depth that we have moved happens to be r minus d. Now here, effectively, because of something called as shell theorem, only the interior sphere, namely this part of the earth, this particular part of the earth that is drawn in white, only the interior part of earth is going to actually exert a net gravitational field on this point. This external annular spherical region is not going to exert any particular gravitational field at this point. So let us understand what is the expression for acceleration to gravity at this point. We know that acceleration due to gravity inside a sphere is equal to gm upon r square into r upon r, where small r is the distance from the center of the sphere. So small r happens to be this particular distance. So in this case, small r is capital R minus d. So GD in this case is going to be equal to Gm upon R square into capital R minus d whole divided by R. Gm upon R square happens to be G naught. So GD is equal to G naught 1 minus d upon R. So this pretty much is the exact expression, and we do not need any approximation for this expression. So this is the exact expression. We can deal with the exact expression over here. So this expression is exact. GD, acceleration to gravity at a depth d below the surface of the earth, happens to be G naught 1 minus d upon R. Now the earth is rotating around its axis as well with an angular velocity omega. Omega happens to be equal to 2 pi radians upon 24 into 60 into 60 seconds. So this comes out to be 2 pi radians upon 86400 seconds. So because of this, all objects on the surface of the earth experience a centrifugal force that tends to throw them outwards. So let us say this is the center of the earth over here, and let us say we are analyzing a point that is over here. Now this point is moving in a circle as shown. It's basically moving in this circle. So this point will be thrown outwards because of the centrifugal force. So let us say this is the radius of this particular circle. The radius of the earth happens to be r, then the radius of this particular circle happens to be, we'll draw the angle requisite. Okay, so basically let us say this angle happens to be theta. This angle is theta. Then in such a case, the radius of the circle around which the point is moving happens to be r sine theta, where r is the radius of the earth. So essentially along this circle, this is r sine theta, and the object is moving with an angular velocity omega, so it will be thrown outwards with a centrifugal force of m omega square r sine theta. Now this particular centrifugal force will have two components. One will be this component away from the center of the earth, and one will be a component tangential to the earth. So this angle being theta, we can find out that this particular angle is theta and this angle is theta because of parallel lines and corresponding angles of parallel lines being congruent. So basically this particular force, that is the centrifugal force m omega square r sine theta, will have a component away from the center of the earth, and this particular component is going to be given as m omega square r sine theta, and one more sine theta will be multiplied, so it is sine square theta. M omega square r sine square theta will be the away from center of earth component of this particular force. The towards the center of earth component is m into g naught. So the net force that the earth is essentially exerting towards the center on a particle that is situated at this point and rotating along with the earth with angular speed omega will be given as force towards the center is equal to mg naught minus m omega square r sine theta into sine theta. Now if I were to find out acceleration due to gravity at that point, then I can say this is equal to mg. This force happens to be equal to mg. So cancelling out m from the entire equation, I can write down g effectively at angle theta. So g theta is going to be effectively equal to g naught minus omega square r sine square theta. Sometimes this particular angle alpha is mentioned instead of the angle theta. In such a case, we can write down g alpha to be equal to g naught minus omega square r cos square alpha, because alpha plus theta is 90 degree and hence sine square theta is going to be equal to cos square alpha. So these are the exact expressions for variation of acceleration due to gravity because of rotation of earth. Now the earth happens to be a bulging sphere. So basically it is because of centrifugal force, the radius of the earth at the equator happens to be slightly more. So this is the radius of the earth at the equator. This happens to be slightly more than the radius of the earth at the poles. So RE is greater than RP. Because of that, we can understand that G happens to be equal to Gm upon a radius of the earth square. So radius of the earth at equator will be Re. So G at equator will be Gm upon Re square. G at poles will be equal to effectively Gm upon Rp square. So G at equator is going to be less than G at pole, because R at equator is greater than R at pole as shown in the diagram. So G at pole is greater than G at equator. So the difference is approximately 0.018 meters per second square. So G at pole happens to be approximately G at equator plus 0.018 meters per second square. So this is the difference between the two. So whenever a body is shifted from the equator to the pole, the weight of the body, which is the net gravitational force that the earth exerts on the body, that weight increases essentially. So we have seen the variation of acceleration due to gravity because of height, because of depth, because of rotation of earth, and because of bulging of earth. So this is why acceleration due to gravity varies on, in, and around the surface of the earth.